all, welcome back. So today we will solve all the questions from sets and relations which came in different shifts of April 2025 attempt. In sets and relations we have total 7 questions, out of which 3 are easily doable and 4 are moderate, which we are going to solve. And this difficulty level is basis my perception, which may be different for others. So let's jump on to our first question. Here is our first question now. This time our question says, let A be the set of all functions integer to integer and R be a relation on A such that this is our relation R, then R is. So here in this question we need to find out that if our R is reflexive, symmetric or transitive. First we will check reflexive. If our R is reflexive or not. So for our R to be reflexive, F, F belongs to R. If F, F belongs to R, then F of 0 is equal to F of 1 and F of 1 is equal to F of 0. So from here, our function of 0 is equal to function of 1, which is not always true. So in this case, this is not always true. So from here, we can say that our R is not reflexive. Now we will move on to symmetry. We will check that if our R is symmetric or not. Now symmetric says F, G belongs to R, then G, F also belongs to R. To check that F, G belongs to R, then we will get F of 0 is equal to G of 1 and F of 1 is equal to G of 0. And if we will have or we can say that directly, and if G, F belongs to R, then we will get G of 0 is equal to F of 1 and G of 1 is equal to F of 0. Now we can see that this is N. Here we can see that these two conditions, both above and below, are same. So from here, if F, G belongs to R, then G, F also belongs to R. This means that our R is symmetric. Now the last, transitive. For transitive, our F, G, if F, G belongs to R and G, H also belongs to R, then F, H should belongs to R. So if F, G belongs to R, we will get F of 0 is equal to G of 1 and G of 0 is equal to F of 1. F of 1 is equal to G of 0, consistent. And for the second case, we will get G of 0 is equal to H of 1 and G of 1 is equal to H of 0. From here we will get F of 0 is equal to H of 0 and F of 1 is equal to H of 1. Now if this condition satisfies, F and H satisfies this condition, but in the question we have given a different condition. So our F comma H does not belongs to R. From here our relation is also not transitive. So our answer is symmetric but neither reflexive nor transitive. And here is our solution, and we can see that our answer is correct. Here is our next question now. Our question says, let A be the set well there is a mistake. This is not 1 to t. This is not till 10. It is till 100. 1 to 100. 100. And R be a relation on A such that R is equal to this. Let these pairs be a sequence of k elements of R such that the second entry, like the second entry is A2, will be of an ordered pair is equal to the first entry of the next ordered pair. Then the largest integer k for which such sequence exists is equal to. So this is a little bit interesting question. First, here in this question we will expand R and we will write the sequence in terms of lambda. So first let's write R. We are making R with respect of B. If B is equal to 1, A will be 3. And if B is equal to 2, A will be 5. And so on till if our B will be 49, then A will be 99. And this will be the maximum value because our set A is from 1 to 100. So here we have our R. Now let's write our sequence. Let's start from here because we are writing in reverse order. Let's say our B is lambda. Then A will be 2 lambda plus 1. Next pair will be 2 lambda plus 1. We are writing in reverse order. So A will be 4 lambda plus 3. And if our B is 4 lambda plus 3, our A will be 8 lambda plus 7. And the next 8 lambda plus 7, we will get 16 lambda plus 15. And let's continue the series below. 16 lambda plus 15, we will get A as 32. 16 lambda plus 15, A will be 32 lambda plus 31. And the next term, 32 lambda plus 31 and 64 lambda plus 63. For now, let's write it till here. Well, let's check if this follows the above requirements. Second entry of the ordered pair will be the first entry of the next ordered pair. Yes, it follows. Now our lambda can be 1 and also 2, so on. First, we can solve this logically. 64 lambda plus 63. The minimum value of this expression, 64 lambda plus 63, will be if our lambda is equal to 1, which is min value is equal to 64 plus 63, 127. So from here we can say that our max to max terms will be 1, 2, 3, 4 and 5. Now let's check it by putting values. Lambda is equal to 1, all satisfies, leaving this 5. Lambda is equal to 2, 64 plus 31, yes, it also satisfies, again 5. And if lambda will be equal to 3, we will get 4 terms, and so on, this will go shorter. So from here we can say that K max is equal to 5. From here our answer is option C, and here we can see that our answer matches correctly. Please wait a minute. This is not 10, this is 1, 0, 100. So here is our next question now. Please wait a minute. Yes. This time our question says, let A is equal to this set. Let R be a relation on A defined by X, R, Y. If and only if this condition exists, let L be the number of elements in R and M be the minimum number of elements required to be added in R to make it a reflexive relation. Then L plus M is equal to. So we can write this expression as minus 2y greater than equal to x square less than equal to 4 minus 2y. Now we will start putting y equal to minus 3, minus 2, minus 1, 0, 1, 2, 3. Then our x square will be between 4 plus 6, 10, 3 into 2, 6, 4, 8, 2 is greater than less than equal to x square is less than equal to 6. 0 is greater than equal to x square is less than equal to 4 minus 2 x square is greater than equal to less than equal to 2 minus 4 less than equal to x square less than equal to 0 minus 6 less than equal to x square less than equal to minus 2. Now Here our x will be belongs to. Now our x is also from the set A, so x will be minus 3 comma 3. Here x will be minus 2 comma 2. Here x belongs to again minus 2 comma 2. Here our x belongs to minus 2 minus 1 0 1 2. Here x belongs to minus 1 0 1. Here x belongs to 0 and here x does not exist. X does not exist. So from here our R is equal to minus 3 minus 3 minus 3 comma 3 minus 2 comma minus 2 minus 2 comma 2. Please wait a minute. Yes. Minus 1 comma minus 2 and minus 1 comma 2 0 comma minus 2 0 comma minus 1 0 comma 0 0 comma 1 and 0 comma 2. 1 comma minus 1 0 comma 0 sorry 1 comma 0 1 comma 0 and 1 comma 1 and last 2 comma 0. Now let's count 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So from here our L is equal to 15 and M first we will check to make it reflexive. We need to add minus 1 comma minus 1 0 comma 0 1 comma 1 2 comma 2 and 3 comma 3 2 comma 2 and 3 comma 3. So from here M is equal to 3, L plus M is equal to 80. So from here our answer is option D. And here we can see that our answer matches correctly. Here is our next question now. This time our question says let A is equal to this set and R be a relation on A defined by X, R, Y if and only if y is equal to max x or 1. Let L be the number of elements in R, M and N, the minimum number of elements required to be added in R to make it reflexive and symmetric relations respectively. Then L plus M plus N is equal to A. We can write our R is equal to minus 2 comma 1 minus 1 comma 1 is 0 comma 1 1 comma 1 2 comma 2 and 3 comma 3. So here number of elements will be 1 2 3 4 5 6. L is equal to 6. If our L is equal to 6, yes, so now we will check if it is reflexive. For reflexive, number of ordered pairs we need to add will be minus 2 minus 2, minus 1 minus 1 and 0 comma 0. So n is equal to 3. And for symmetric, we need to add 1 comma minus 2, 1 comma minus 2, 1 and 1 comma 0. So from here our n is also equal to 3. So we will get L plus M plus N is equal to 6 plus 3 plus 3, 12. So from here our answer is option A. And here is our solution and we can see that our answer is correct. Here is our next question now. Now this question is similar as the previous question. So our question says let A is equal to this set and R be a relation of A defined by X or Y if and only if this condition exists. Let L be the number of elements in R and M and N be the minimum number of elements required to be added in R to make it reflexive and symmetric relations respectively. Then L plus M plus N is equal to so here in this question, first 2x minus y is equal to 0 minus y is equal to 0. Then our ordered pairs x comma y will be 0 comma 0, 1 comma 2 and minus 1 comma minus 2. If our 2x minus y is equal to 1, pairs will be 0 comma minus 1 and 1 comma 1. Other pair will be 2 comma 3 and the last minus 1 comma minus 3. Yes. So from here R is equal to 0 comma 0, 1 comma 2 minus 1 comma minus 2, 0 0, minus 1, 1, 1, 2, 2, 3, and minus 1, minus 3. So let's first count number of elements. 1, 2, 3, 4, 5, 6, 7. So here L is equal to 7. Reflexive. To make it reflexive, we need to add minus 3, minus 3, minus 2, minus 2, minus 1, minus 1. We have 0 and 1, 2, 2, and 3, 3. 1, 2, 3, 4, 5. So our n is equal to 5. Now for symmetric, we need to add 2, 1, minus 2, minus 1, minus 1, 0, 3, 2, and minus 3, minus 1. So from here our n is equal to 5. So L plus m plus n is equal to 17. From here our option B is correct. And here is our solution, and we can see that our answer is correct. Here is our next question now. This time our question says the number of relations on the set A containing at most 6 elements, including 1, 2, which are reflexive and transitive but not symmetric. So here in this question, elements 1, 1, 2, 2, 3, 3, and 1, 2 are in R. Then our remaining elements, remaining all pairs. So let's just write remaining will be 2, 1, 2, 3, 1, 3, 3, 1, 3, 2. So our case 1 will be 4 elements. In case 1 we have 4 elements, so here number of ways will be the above 4 elements, so only one way. Case 2, 5 elements. Now we have to maintain its reflexive and transitive property and add elements. So we can add 1, 3 or 3, 2. 1, 3 or 3, 2. So in this case number of ways is equal to 2, and case 3 is 6 elements. In that case, we have 2, 3, comma 1, comma 3. Other case is this one, 1, comma 3, and 3, comma 2, and the last one, 3, comma 1, and 3, comma 2. So in this case, number of ways is equal to 3. So our total ways is equal to 1 plus 2 plus 3, 6. From here, our answer is 6. And here is our solution, and we can see that our answer is correct. Here is our next question. This time our question says, let A be the set, let R be relation on A defined by this, if and only if max of x comma y belongs to 3 comma 4. Then among the statements S1, number of elements in R is 18. And statement 2, the relation R is symmetric but neither reflexive nor transfer. So first let's write our relation R. Our R is equal to 0, 3, 3, 0, 0, 4, 4, 0, 1, 3, 3, 1, 1, 4, 4, 1, 2, 3, 3, 2, 2, 4, and 4, 2. Please wait a minute. Yes. And 3, 3. And then we will have 3, 4, 4, 3, 3, 4, and 4, 3. And the last 4, 4. So here let's count number of elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So from here, number of elements in R is equal to 16. From here, we can say that case 1 is rejected. Now, for case 2, our R. So, as we have written pairs, stepwise our R is symmetric. But not reflexive, because we don't have 0, 0, 1, 1, and so on. So it is symmetric but neither reflexive reflexive and this is not case 1, this is statement 1. Neither reflexive nor transitive. Also we can check transitivity. 1, 4, 4, 1. It will be 1, 1, and 1, 1 is not in the set R. So from here our statement 2 is correct. So from here our option C is correct. And here is our solution. And we can see that our answer is correct. So hope you found this video helpful. Thank you for watching.